Well, a warm welcome to you all, young and old, beginners and experts, and I'm pleased to say Ben in North Carolina, amongst others. This evening, we particularly welcome our guest and speaker this evening, David Hendricks, who will give us an overview on the topic of gravitational waves. After a short introduction, he will cover the theory of gravitational waves and show which systems and phenomena would emit gravitational waves. David is a PhD student at the University of Surrey, where he works under the guidance of Dr. Robert Izzard in the Surrey STARS team. His current research focuses on the interaction between binary stars and accretion disks, specifically the loss of material from accretion disks and the impact that this has on the orbital evolution. He obtained his bachelor and master's degree at the University of Amsterdam after doing his master's thesis on synthetic models of black hole populations and the impact of pulsational pair instability supernovae on the observable gravitational waves from these black holes. As you will gather or might imagine, he's originally from the Netherlands. He has 3 siblings that still live there. He likes to code, listen to music, and ride his bike without his hands. David, the floor is yours.
Yes, thank you for that introduction. All right, so let me share my screen. With previous presentations, I noticed that my camera, if I have my camera on, sometimes my Zoom crashes. So I'll put my video sharing off, but my screen sharing is on. Do you see the slides or the, yeah? All right, so I signed up to give a talk about one of 2 topics, either binary stellar evolution or gravitational waves, and the preference went out to gravitational waves. So I'm not sure how many talks you've had about this topic already, or how much you know about this topic. I gather that you are all astronomers in some sense, and do observations with personal telescopes or with institutes. Generally, the objects that you will observe through this are not the same as gravitational wave emitting objects. So I hope I will be able to tell you something interesting today. So indeed, I work at the University of Surrey. I think you all know that place. Is that the home base for the society?
It is.
Yeah, okay. Well, whenever it's opened again, then you will probably see me around. Yeah, so let me start with the topic. Okay, so I will give an overview of the topic of gravitational waves. I will start very, very compactly with the theory of gravitational waves. Then I will explain some of the methods of observation. More interesting afterwards, the sources that can emit these gravitational waves and the different forms that these gravitational waves can be observed in. Then I will show a couple of the recent observations and some of the current studies that I was distantly or closely related to in my work. So small disclaimer, this field of gravitational wave astronomy is a field that's growing rapidly, but it's already quite big. To cover everything in a short lecture like this is way beyond the scope of this talk. So I will give a broad overview mostly. So yeah, I thought it would be useful to start with just explaining what a gravitational wave is. This is a ripple in space-time, and that might seem a bit abstract, but it effectively can stretch or squeeze space. and it behaves like a wave, much like a wave on the surface of water. So this gravitational wave is sort of the communicating method for gravity, just like light is for electromagnetism. And one of the, well, maybe annoying properties that it's very difficult to measure. And I wrote here that the typical strain, is my pointer visible, by the way? It is, right? I assume it is then. Okay, so the typical strain, the strain is effectively what the measure of expansion or contraction of the space, is on the order of 10 to the minus 21. And that's really, really small. The analogy is made between the distance to the closest star, Alpha Centauri star system. If you would measure that distance with the accuracy of a human hair, then that would be comparable to the accuracy of measuring this strain. I thought another maybe more fitting way is to take a local body of water and to say, okay, if we take a bottle cap out of the Loch Ness Lake, a bottle cap more or less 5 milliliters, then a billionth of that 5 milliliters versus compared to the total volume of the Loch Ness would be the accuracy. It's just really small. And the fact that we now have been able to actually measure these things is very, very wonderful. Yeah, it's very amazing that we can do this. So gravitational waves was, it's been coined to Einstein. Credit was given to him in that sense. It's based, it comes from the general relativity theory. It was sort of predicted by Einstein in 1916 already when he published his work on general relativity. It wasn't really a fully developed model yet. A better derivation was done by Einstein as well in 1918. But even though he actually derived this, he was not very sure of the existence of the gravitational waves. And he predicted a couple of forms of this. And not all of the forms were actually physically real. So it still took a couple of decades before the full theory was developed properly. However, before Einstein proposed or predicted this, there were other people that discussed this, like Oliver Heaviside and Poincaré, where, well, so they sort of took the analogy with electromagnetism and postulated that there should be something as gravitational waves in the theory of gravity. However, they did not have the general relativity framework to really work this out. But Einstein was not the first one to really think of the general idea of gravitational waves. If we would observe these gravitational waves, it would be yet another success for the theory of general relativity. Well, small spoiler we have, and I think everybody knows that already. But one of the good observables and one of the effects that gravitational waves have on, for example, a system of orbiting stars or orbiting planets or anything orbiting each other, is that the decrease in period because of this gravitational wave emission is accelerated. They get closer and closer, faster and faster. And this goes for every object that's orbiting another object, essentially. However, it's only really strong enough to do something in the lifetime of the universe for massive compact objects like neutron stars or black holes. Otherwise, it would just take way too long. So as I said, a test subject that would show this would be double neutron stars. And neutron stars are easier to spot than black holes because they do emit light or in the form of a pulsar or just thermally. So we could observe these double neutron stars, and in 1974, I think it was the Hulse and Taylor that observed the binary pulsar that actually showed this orbital decay exactly how it was predicted. They later got the Nobel Prize for this observation as well. And this is the observation is not from the same paper, I think, but the line is the prediction of general relativity that if gravitational waves would actually exist, that this is what we would see, and this is exactly what they saw. So that was a big success for the idea of gravitational waves. It was, however, an indirect measurement, and it would still take quite a while before we actually could observe these waves directly. Regardless, observing this indirectly sparked a big, a hype, enthusiasm for continuing this research. Sadly, however, all of the attempts up until more or less now have failed to observe any gravitational wave directly. I was surprised how many devices or observatories were actually made in order to measure this. And it started in the early 60s or early 70s already with this. But it took until 2015, so 40 years later, to directly observe this. So we now have more or less 50 direct observations, which are all confirmed. There is a list of observations that's, their sigma is not high enough to say it's a direct, it's a real observation, but we have good reason to believe that they are also real signals. And it's only going to get more, so we should stay tuned, because this is like the start of an era. And I think this is really exciting because gravitational waves, it provides a new way to observe the universe in a way that's in some ways better. So gravitational waves hardly interact with matter. They do a bit, because otherwise we would not really be able to observe it. But they don't interact the same way as electromagnetic signals. So the signal that we see is more or less the pure signal, how it was created. There is hardly any reddening, for example. It's also good that it's not obstructed by the atmosphere, so we can have observatories on Earth to observe this. That is good. So the signal is pure. It was how it was created. But on the other end, we also will be able to detect things that do not emit any light. Like, for example, black holes merging. These will in general not emit any light. And for example, primordial gravitational waves, things happening way back in the early stages of the universe. It will provide a new way to measure the expansion of the universe, to measure the Hubble constant, which is also interesting because there's a bit of a tension in this Hubble constant now. There's two different independent measurements of this Hubble constant, and they do not agree. And it will be very interesting to see what the gravitational wave determination does for this. And it's been said that observing gravitational waves is a little bit like listening to the universe. It all has to do with vibrations. So we sort of really got a new like a sixth sense, like a new sense to observe the universe, and I think that's really exciting. Okay, so very ambitiously I included this part, but then I realized that if you really want to cover this properly, it just takes like at least 4 lectures to go through all the mathematics, and we don't have time for this. Okay, so roughly how we can derive gravitational waves is by the method called linearized gravity. And so, okay, what we see here on the right is first equation. These are the general relativity equations. These are highly nonlinear and these are coupled. And that's very difficult to solve, and you need very strong computers to do this, or very ideal situations. So it's just difficult. You can, however, sort of say, okay, well, what if the gravitational field that we're in is not strong? And it's called the weak field approximation. In essence, we're in a vacuum. There's no gravitational object nearby. That is then a flat spacetime. It's just a Minkowski spacetime. That's the second equation here, where this is just flat spacetime. And then we say, okay, we take a small perturbation on this. This is very analogous to just perturbation theory, where you can derive, for example, the speed of sound through a medium as perturbations in pressure and density. It's very similar. It takes a different framework and different changes in parameters, and there's between these steps, well, these two are the start and this is the end, and between those steps are a lot of steps. However, this symbol here is it's called the Lambertian, and this is well, how do I say this? It's sort of this is the standard symbol for any wave-like equation, be it one-dimensional or three-dimensional or two-dimensional. And then you can derive from this how the wave should propagate through space. It's important to note that only in a situation where there's a change in quadrupole moment, and that means more or less that the mass, so the orientation and the mass changes in space, like the location, but only if you have, for example, a binary system or a deformed neutron star. So if you have a pulsation which is totally spherical, that will not emit any gravitational waves. And so this is a nice constraint already on the types of sources that can emit gravitational waves, for example, binary stars. If you would solve this previous equation, this one, with a lot of steps in between, then you can derive that there's two different types of waves in here. There's a transverse wave. No, it is a transverse wave with multiple polarizations. This is the plus polarization. This is the X polarization, and these propagate through space. If you combine these two, you get strain. It's just a combination of these. They are expected to travel at the speed of light, and we actually observed it to be the case. There are models and derivations that predict something else, but these are a bit niche. And the amplitude of this strain, sort of, this is the thing that we observe, the expansion of space. It falls off as 1 over r, unlike any observation made from photons. If something is 10 times further away, it gets 100 times dimmer. So this is a 1 over r proportionality, 1 over r squared for the photons, but for the gravitational waves, 1 over r. That means that they just fall off less quickly, and we can observe a bigger volume than, for example, with photons. This is everything that I am going to say about the theory of gravitational wave. I just want to show we take Einstein's general relativity, we linearize it, and then we perturb space-time, and then we get waves. And that's the very small gist of it. And I think that's enough. So I said this a couple of times already, but if we want to observe gravitational waves, we should observe the squeezing and stretching of space. And the strain is directly related to this squeezing and stretching. And if we observe any squeeze or stretch, we can conclude something about the strain of this gravitational wave. And the change of this strain, the change of this squeezing and stretching, that will be able to tell us something about the source or the event. And it pays off to listen continuously for these signals, because they will come in from all directions the whole time. And the universe is actually just filled with this squeezing and stretching of space, and it's very difficult to weed out these signals, but we're getting better at this. There's two general ways to do this. This is called the free mass method and the non-free mass method. The free mass means that there's, okay, you have two objects, but in between there's nothing that connects them. It's just empty space or, well, air, for example, but there's nothing that physically connects them. The non-free mass is then the opposite. There's actually well, elongated object like a bar or a sphere that's actually connected all the way through, like a solid object. That can also be affected by these gravitational waves. Generally, with these detectors, especially with these laser interferometers, the more of them you have, the better it is. Because all of these detectors, they are very prone to noise. As I said, that the signal that we should measure is on the order of 10 to the minus 21. If you would drive past the experiment with a truck, that will mess up this. However, if you have more of these observations or more of these observatories or detectors, then you can weed out any local noise at one detector, and then you can correlate the signal still. And then that's why it's better to have more detectors to sort of weed out all the noise that is locally at one detector. So I'll start with these resonant bar detectors, which are like the non-free mass detectors. I think, well, they were sort of both thought of at the same time, but these were the realized the earliest of the first, I think, in the early 70s. So this is a solid object, and this solid object can expand and contract or squeeze and stretch. However, there's other forces that prevent the particles in this object to really follow the geodesics. The geodesics is just the path that the particle in spacetime follows. There's, okay, so you can sort of see this as a forced oscillator. We have an oscillating object, and we have a forcing, which is then this is the strain that changes over time, which can be seen as a force, and this can excite waves in the object. And if the object is designed to fit well with the for example black hole mergers, you can design it to get excited on a resonance, and then we can sort of amplify this vibration through the object to a visible vibration. So however, what I already said, these detectors are prone to noise, and so this extra object here, this is another force, and this force is anything that can disturb this thermal noise, outside fluctuations, a driving car past, or earthquakes, or whatever. To prevent this from messing up your experiment, generally you would want these objects to be very cold to reduce all the thermal noise, and isolated, suspended, to eliminate all the outside fluctuations. Yeah, so the early models were made in the 60s, I think, because it was just easier to construct these objects, at least. Well, initially they thought this detector brings with it a lot of technical difficulties, and this is by no way an easy experiment to do. So a lot of them were actually bar configurations, which was elongated objects like a bar, generally quite massive, and they had to be cooled down. Some of them actually were spherical, like this one in Leiden, which is called the mini grill. It has the advantage of not having a preferred direction through which the gravitational wave should travel in order to be measured. So because this is like symmetric, it could detect gravitational waves in any direction. However, I'm not sure if any one of these has actually measured a gravitational wave, like that we know for sure that it happened. So as I said, these can be tuned, and it depends on the material that you make it with. These can be tuned to like specifically tuned for a certain event, like a gravitational, like a black hole merger or supernova. But again, I don't think they've been successful. There are still several active experiments, like the mini grill or the Nautilus. And in the past, there have been quite a lot, and I'm sure I'm missing other efforts on this list. I think I will share the slides, and on some slides I have references to papers that are useful. So if you want to look up, this is a very nice paper that explains all the details behind it and all the sort of the future and the current state of this type of detector. So now to the maybe more familiar detector, it's called the laser interferometer. Instead of using resonances within the solid object itself, we use a laser that interferes with itself or well, interferes with its sibling beam. I think it's easiest, this cartoon actually shows it quite well. So as I showed, there's these types of waves, and this is the plus wave, the H plus, which makes the space-time stretch in the decent distance up and down and left and right. And if you have a detector which is aligned with this with these axes, then you would have the arms stretch and then the other arm stretch. Now, if you run lasers through these arms, then okay, so the light actually gets stretched as well, but with some very clever tricks, they are still able to create a changing interference pattern. So you start out these lasers either totally in phase or totally out of phase. So you know what the baseline interference pattern should be. And any change in this interference pattern, which is going to be very small, which would then inform you of the strain or the sort of the expansion of these arms. There's a reason this took quite a while for scientists to do. It's just technically very challenging. You want to have very long arms. The arms of the current detectors are like 4 kilometers more or less. If you shoot a laser through this, you want to have a vacuum, because otherwise the laser will, well, it will heat up the air inside and it will scatter the light all over the place. It's not going to work very well. Again, we have the same issue. We need to reduce the noise, so we need to hang up the mirrors that deflect the light back to suppress all the noise. And there's a lot of effort to suppress the noise, and they're doing an amazing job to actually suppress it. They're really getting it down to design sensitivity now. And for example, the mirrors need to be perfectly smooth, and it's just all of these things are like technological wonders that they actually managed to do this. Another overview of a setup like this. This is, well, mimicked either one of the LIGO detectors. So here we have the arms, here and here, and there's a beam coming from the laser source, and the laser source gets split into two. Here at the beam splitter, one half more or less goes there, the other half goes there. And if a wave passes through, then either this arm expands, for elongates, or this one. And when the lasers travel back and hit this plate, then this photodetector will observe an interference pattern that's changing if a gravitational wave comes through. I said they were really doing a well job at reducing the noise. Here we see sort of the sensitivity curve of these detectors. These are LIGO and Virgo, Livingstone, and the other one I forgot the name. But they got it down to in the best position to 10 to the minus 23, which is a very, very sensitive. But we have these spikes in between, which are just like fluctuations of all kinds of things and quantum fluctuations. At some point, we're hitting the level that we cannot make this better anymore, and we need to do the next thing, which I will show in a bit. So there's currently 3 operating detectors. One for a while already, which is the GEO 600, which is 600 meters long, which is in Germany. Sadly, this one hasn't detected anything, but I'm not sure if it was really expected for this one to detect anything. It's like the ITER, which more or less like, okay, well, it's a proof of concept. Let's see what we need to do to make it even better. And then here are the LIGO and Virgo. So this is LIGO Hanford, this is LIGO Livingstone, this is the Virgo in Italy, and this is well, it's not online yet. It is online, but not in the combination of all 3. This is the one in Japan, which is underground. And so here we see the frequency range that these detectors will operate best in. And these shaded areas, these are like the areas of certain sources. This pink, well, they are all kind of pink. The leftmost here is for compact binaries like black holes and neutron stars. Then we have these bars for the supernovae, and the pulsars are also in this range, but just about. And so a LIGO is the advanced LIGO with all the upgrades. I think that's operational now, and so we should be able to at some point go and see supernova happening as well. This here is the LISA mission, which is the next step in these detectors. So it's still a laser interferometer. However, this time it's in space. The plan is to put 3 satellites in space. Let me see if I think I'll show this one first. So there's this. They're going to put 3 satellites in space, and that's orbiting the Earth. And the arm length is now 10 times longer, no, 1,000 times longer, 2.5 million kilometers. Where there's one of them is the signal sender and receiver, and the other 2 are the mirrors, so to say. As you can see, it operates a little bit in a different range than LIGO itself, because the arms are way longer. It's sensitive to different frequencies, and also then different sources. So we have galactic binaries, but now not in the merging phase, but way before they're merging, or very massive binaries in the galactic centers, or binaries with a very unequal mass, where there's a 50 solar mass binary orbiting a 1 million solar mass star of a black hole. So there's a couple of advantages of going to space. One of them is we get a vacuum for free. That's very nice. But well, going to space has its own challenges. There's a lot of cost of putting something in space. It's difficult to repair if something breaks down. And then we have the solar wind, for example, radiation coming from outer space, cosmic rays. Planets are also a problem. If you make these arms too long, then the perturbations that planets can have on these satellites will also be significant. There's debris floating in space. This I didn't know actually, but these satellites, they are designed, or they're going to be designed as zero drag satellites, which sort of means that the detector itself, that's measuring the light from the other 2, will be free floating in space, and the satellite is just floating around it. And so if the satellite gets a small push from solar wind, the detector within the satellite is not affected, and the satellite will then accordingly push the other way to compensate for the impulse that the solar wind gave. But the detector itself inside is not affected by this push. So the LISA mission is expected to launch in 2034, which probably gets a little bit later, maybe a couple of years later then. And what this is supposed to observe is continuous galactic binaries, so binary black holes, for example, but way before they will merge, white dwarf systems, supermassive black holes that are actually inspiraling. But it's also able to already measure the background and potentially measure expansion of the universe through other sources like supernova that go off way in the distance. And then there's a special one, which is on an even bigger scale. It's called the pulsar timing array. So what we did with the other two was, okay, we have a signal and there's path length change, and so the signal arrives a little bit later. We can do the same thing with pulsars, where we know when the signal should arrive, and if that changes, then there is something going on. And now these millisecond pulsars, they're very stable, so they will be good sort of clocks to work with, and they also don't have a lot of disturbing factors like starquakes apparently. And any change in this arrival time will sort of inform us about very long wavelength gravitational waves. Now with this, it's very difficult to measure the location of any signal, where it came from. But it has other advantages. It can measure things that happened way early in the universe. It can measure the background. I think there are efforts already going on for this, the Parkes PTA and the European Pulsar Timing Array. And they usually take like 20 to 30 pulsars as like the orientation, and then calibrate everything. And then if something travels through, this is a very interesting topic, but quite difficult as well. So now onto the sources. I a couple of times already about binaries that merge at supernova. So we can ask ourselves the question, okay, what kind of signal do we expect to observe? If it's a wave, it can be a short wave, sort of like a burst or a continuous wave, or just noise in the background. And then we can ask ourselves, okay, which kind of phenomena produce these gravitational waves? So the continuous gravitational wave signal is just like a flat note. You just hear the same tone the whole time, or see the same tone. The in-spiral signal is sort of the chirp that you know, the whoop. That's the ones that we observed already. Now the burst signal is expected to come from supernovae, and stochastic signal is all the background, everything. So here's an overview of so the top is the sources, which things sort of create the observations that we the things that we can observe. We are here now with the terrestrial interferometers, and we can observe rotating neutron stars, supernovae, and in-spiraling black hole binaries. With the space interferometers, we can look for the more massive objects and the continuous in-spirals. And with the pulsar timing arrays, we can also have the supermassive black holes, but also the quantum fluctuations and all the things that happened in the stochastic background. And just like normal light-based observations, we have the whole range, the whole spectrum of frequencies that things are happening on. And there's a merit in putting observatories that cover different wavelengths, so to say. Even the cosmic microwave background can be a tool for us to measure things. The polarization of this could tell us something about gravitational waves in the early universe. There has been a claim from the BICEP experiment that they found polarized cosmic microwave background. In the end, that was debunked. It was not a real observation, but we could still find that. So the continuous gravitational waves, as I said, this is actually just like a constant tone. And this is emitted by systems that are just orbiting each other, but not getting closer very fast. Like double neutron stars, double black holes. But also, for example, a neutron star, which is very rapidly rotating and has a deformity. like a mountain which can be made by magnetic fields that would exert tension on the crust, for example. So this usually the signal is not very strong. It's like a baseline tone, but it's not very strong because the event is also not very catastrophic. We will see in the other sources that there are more intense signals. So we do see here a variation in this wave. So if I'm correct, this lowest. So okay, so the Earth is rotating. This is something that modulates the signal already because it sort of Doppler shifts the signal. Then the Earth is rotating around the Sun as well, and then we have the original wave, and this is then the original wave. So now the one that we are more familiar with is the in-spiral signal. This is the moment that two objects get so close that their in-spiral is just accelerated and they will merge very quickly. I must say, okay, I wrote down this is relatively easy to detect in the data, but the emphasis on relatively. Detecting any of these signals is actually very difficult and requires a lot of very clever techniques and a lot of computing power. This signal is stronger because when these two objects merge, for example, if you have two black holes of 30 solar mass, there's more or less 3 solar mass that does not end up in the final mass of the merged object, but 3 solar mass of pure energy that gets irradiated as gravitational waves. And so this is a way more catastrophic event, and a lot of that energy goes into the emission of these gravitational waves. This signal is sort of composed of three parts. This is the in-spiral part, well, up until here, I think, and then we have the merging part where the objects really collide. They are still deformed, and then when they sort of relax onto their final shape, that's called the ring down, and then the signal flattens, then there's no signal anymore. So this first part we can actually do with called post-Newtonian techniques. We sort of approximate general relativity with clever tricks, and we introduce higher order approximations of velocities in here. The merger itself and the ring down we cannot do with post-Newtonian techniques, and then we really need to have full general relativistic computer simulations of this. This is difficult, but people are definitely doing this, and they have made a lot of these. This is called a waveform, and what they do, they take a whole suite of masses and a whole suite of, for example, spins of these objects or precessions of these objects or eccentricities, and they calculate what the waveform should look like. And what they then do is they save all of this waveforms in like a big template bank. And if they observe a gravitational wave, or they think, they will run all of these waveforms as like a sort of comparison and then try to find the best fit. There's a lot of statistics going on there, but they do manage to find good fits. And so the exact waveform, as I said, depends on the properties of the system, like the mass, the deformability. If we're talking about neutron stars, that has an effect on this, very small effect in some cases, but there is an effect. Then there's this quite interesting one. It's called the burst gravitational waves, things that go bump in the night. We cannot really predict these because the signal travels as fast, maybe even arrives earlier than the light of a supernova. So it's also difficult with what shape they will have. So this is generally produced, so the gravitational wave emission from this is produced by the convective motion of the material in this supernova, partially. So here you see these blobs. These are convective motions within the sort of the core of this supernova in the first 100 kilometers. And these are non-axisymmetric motions of mass, so it emits gravitational waves. This is part of the signal, and when all these blobs sort of fall back on the proton-neutron star, this proton-neutron star will begin to vibrate in a certain way that also emits gravitational waves. People are doing this. There are 2 and 3D hydrodynamic simulations or hybrids between this that calculate the signal that we expect to see. However, there's not the full consensus between the different groups yet. So to really distill the general features of what we would see is, I think, well, it still takes a couple of years. If we would see this, that would tell us a lot about the supernova mechanism, though. There is a couple of open questions within how a supernova, specifically core collapses, how they work. And this would be very informing. So this searching for this won't be done with any template matching. That's something I mentioned in the previous slide, where they pre-calculate this, just because we don't really know what to look for. Maybe later we will, if we have more solid modeling of the supernova, then we might do this. And there's surely signals that we cannot predict, because these might not be the only emitting object. And now there's the last sort of the, oh no, this, oh yes, this slide is quite interesting. So this is one of the results of one of the studies that actually calculated the waveform that you would see from a core collapse supernova, where the mass of the core collapse, the mass of the star that explodes just before it explodes, is here at the top left, and it increases when we go down. Generally, we see 2 parts in this. This first part is created by the convective motions. It looks a little bit like the in-spiral merger. And then we have the part where all these blobs fall back onto the neutron star again, and that just becomes very noisy. But these are a set of results from these calculations, and these are examples of what we would see if this object would be at 10 kiloparsec. It would be visible in the bands that we are able to measure in, but well, in some cases just barely, and we would need a new next generation Einstein telescope to actually measure this properly, I think. But who knows, maybe somewhere soon we will find a clear signal that comes from a core collapse supernova, and perhaps with a electromagnetic counterpart signal. That would be very exciting. And then we have the stochastic background signals, which essentially is just the noise, the background noise. However, this can actually contain a lot of information as well. There's parts that shortly after the Big Bang are predicted to emit gravitational waves. Also in parts of time that we cannot observe with light because of the less scattering. When everything was ionized, the light couldn't go through. And gravitational waves would give us a way to peer into that era of the universe. And then there's a whole suite of theoretical predictions that are very exciting and also very difficult to explain. But there's a lot of things going on, cosmic strings, phase transitions. I had a colleague when I was working in Amsterdam that did this project on colliding universes. So if you have the multiverse idea, then these multiverses could collide, and that might emit gravitational waves. But that ventures a little bit out into the theoretical part too much, I think. Okay, and so this is partially made up of all these very exotic theoretical things, and also of all the gravitational waves that we haven't been able to pinpoint or are too faint to distill from this this background. Again, this slide has a reference to an interesting paper that explains this topic quite well. It's quite a long read, though. I have not read it fully. All right. So we have actually observed several of these already, more or less 50, and I wanted to start with the first binary black hole observation, which was immediately quite exciting. So here we see the waveform, the observation of this, and the template that was matched to it. And here is the translated into frequency space. This is the, if you would run this as a sound, then it would be chirp. The interesting thing about this observation already was that these black holes were way more massive than previously known black holes, and I will show that in a bit in a different slide. This discovery was made on 14 September 2015. I was doing my master's. This was quite an exciting time for me, studying topics like this and then actually having the observations happening. This is the localization of this event. So if you have one detector, you will only really measure a plane in, well, a slice. It's just 2D what you're measuring. And if you have multiple detectors, you can actually begin to localize in space where it must have come from. There's a lot of statistics in going, determining where it came from, which direction. But in this sense, the more detectors you have, the better it is. Another interesting one, of course, was the neutron star merger that was exciting in several ways, because we also observed the electromagnetic signal, and that was really a treasure trove in the sense that we could confirm a couple of things, namely the speed at which this wave traveled, but also the light curve that we saw from this kilonova. There was a lot of information in this, and we could now begin to model these light curves. And from this one observation, it was already clear that a lot of the R process elements, which are rapid capture nucleosynthesis elements, very usually high atomic number elements like uranium, platinum, gold, etc. These are formed in these neutron star mergers, and this one observation was sort of enough to confirm this hunch that they already had, but it was good to see this actually happening. So for this observation, we have very, very narrow localization in the sky that actually made it possible to pinpoint the electromagnetic signal as well. And that's because the Virgo observatory was now online as well. So now we have 3 observatories, which make it possible to pinpoint that even better. Yeah. Okay. So in the first set of observations that was sort of released as the definite observations, we can already see some interesting facts here. So first, for the neutron stars, the yellow ones are the electromagnetically observed neutron stars with pulsars or X-ray binaries, for example. And these 2 objects, which seem to be on average the correct mass for that population of neutron stars, they merged to an object which was high, very high. This object probably also either directly collapsed into a black hole or after a short time collapsed into a black hole. But for the black holes that we see, it's actually more interesting because a lot of the black holes that we see merging, for example, they are way more massive than the purple black holes that we see here. And these purple black holes are again black holes that are observed in X-ray binaries, for example. And so we're actually probing a different population of black holes. And one of the reasons is that more massive systems are easier to detect. We can detect them from further out, so the volume that we're probing is larger. So we're expected to find these easier. Now, this is something that I was working on my master's. if you sort of squint, then you can sort of draw a line along this mass here and say, okay, well, there's hardly any progenitor black hole that is more massive than the line here, except for this one. However, all of them have error bars, and this would sort of be in the error bars of being in there or not. And I've written down mass gap question mark because there is theoretical reasons to believe that there is a mass gap or sort of a forbidden area there. And that's what I was working on my master thesis, sort of the supernova engine that creates this gap. However, if we now go to the new set of observations, I haven't redrawn the line here, but the line was actually here. There is actually quite a group of black holes that were already formed and are in that mass gap. I will come back to this later. But there's two very interesting objects in here that I highlighted. This is the GW 190521, which is just very massive, where both of the black holes are fully or marginally inside this mass gap. So this is a very interesting system. It's difficult to explain how this was formed. The other ones are easier to explain. And then we have GW 190814, which is a very, well, it has a mass ratio that's very low. So a neutron star with a black hole, or it's not clear if it's a neutron star, but it's in the other mass gap. Okay, so you can have a whole lecture about this. I will not go too much into this, but these are interesting systems. All right. So there's ongoing studies continuously to explain the observations or to use the observations and explain other things. This is something that I did for my master thesis, where I sort of used calculations and then compared that to the gravitational waves that we saw. So we should first ask ourselves where these black holes come from. So for most of the black holes that we are observing in the range that the detectors are built for, they were originally stars. And then we need to ask ourselves, how do they end up as a black hole? And then the question is actually, how do the progenitors, like the stars that they were before, how do they evolve? And how do they end up in black holes that massive? Then we have the question of, okay, where do they come from, in the sense that, do they come from a cluster, globular cluster, open clusters? Well, there are things that happen to black holes that, if they're in a cluster that is too light, they will get kicked out. So in a cluster that's like an open cluster, for example, or an association, they will not originate there because they will just be flung out. However, in a nuclear cluster around in the center of the galaxy, these are ideal places because the field is so heavy, it's difficult to go out of those clusters. Or are they formed in the field, just in the disk of the galaxy, or in the AGN disk, which is a different kind of disk, which is the accretion disk around the black hole? Or do they form in all of these different places at the same time and more or less in the same occurrence? So this is one of the questions, right? Where do they form most, and what does that say about their evolution and about the stellar physics that we know of? And so what we want to do is we use stellar models that we have, and we combine the stellar single models and binary models, and we put that into a population of stars. And with this population of stars, we go and predict what we would see. And there's a lot of steps in between. Again, this is quite an involved field. So if we observe a set of binaries merging, and we see, for example, that they are in general always around 30 solar mass, except for a certain outlier group, or that all of them always have a low spin, or they're always the same mass, more or less, that infers us about these different channels, so to say. Do they come from clusters that will lead to a different signal, more or less, for the merging stars? They will not be equal mass that much, and they will have different inclinations, whereas in the field they will be both inclined if they have any spin, and they are expected to have very little spin anyway. So by looking very closely to the observations, we can say, okay, well, probably this has formed in isolated evolution, for example. With these observations and knowing the technical details of the detector, we can sort of say, okay, this is the volume of space that we probe, and that if we observe 10 of these gravitational waves per year, that could inform us about the merger rate of the local universe, for example. We could calculate what we would see with the detector and what that would mean for all the observations, all the things that we do not observe. And we usually call it the merger rate. And we can compare the merger rate that we actually observe to the merger rate that we predict. And the merger rate that we predict is depends on a couple of things. Depends on the stellar evolution, where many things are still uncertain, especially for these high mass stars. It also depends on the star formation history, because that just dictates how many stars there are that could possibly end up as black holes. And it also depends on the metallicity evolution. If you have a higher metal content in a star, then that has an influence on the stellar evolution. So as I said, okay, so if we want to make a black hole that is massive, then we want a star that was massive already, and we want it to stay massive. And in general, very massive stars lose their mass very quickly. So the star needs to stay massive, and preferably this then happens in an environment or a location in space or time that there was a low metallicity. A lower metal content in the envelope of these stars prevents the outer layers or envelope of being sort of radiated off, and so it doesn't lose as much mass. Or there's a special evolution in which they rotate so fast that they do not expand. This is called chemically homogeneous. It's very interesting. We do not expect the majority of these systems to come from that, though, but there's surely a population that will come from this. Then the other question, okay, we need to form a black hole and it needs to stay massive, but we also need to form a black hole in a binary which is able to merge. This is possible by either dynamical capture. If there's just a cloud of black holes whizzing around each other, then sometimes they will get so close that they will just capture each other and then sometimes interchange their partners, for example. But for isolated evolution, there's two problems to overcome. These massive stars, they undergo supernovae, and in general, supernovae are accompanied by a kick, which is stronger for lower mass objects like neutron stars. But nonetheless, for black hole formation, there's also a kick exerted on these stars. So they need to survive this kick. And then they have to get close enough to be able to merge in the Hubble time. And for that reason, we think that there's a very big chunk of all the merging binaries that have undergone a common envelope evolution, where at some point one of the stars gets so big that it engulfs the whole system, and due to gravitational drag, they either expel the envelope and end up very close, or they merge beforehand, and then that doesn't lead to a gravitational wave merger, but a different kind of merger. Okay, so how do we make these predictions? How we can calculate the rate that we expect? That's with a tool called population synthesis, in which we sort of parameterize a lot of the stellar evolution into either a table that we interpolate on or into analytic fits. And in this way, we can evolve a binary system from from the birth to their end in 1 second. It's really fast. And my supervisor, Robert Ishart, has written this code called binary C. And in this code, it's, well, I depict it as a black box. And it's not a fully black box. We sort of know what's going on, but the combination of all these interactions sometimes makes for unpredictable outcomes. So we make a choice for the stellar winds, and a choice for the supernova, and choice for the tides, and all of these different physical interactions. And then we say, okay, we take a population of stars that follows the Krupa initial mass function, where very massive stars are very improbable, but we still assign them a probability, and then we evolve them, and then we see what comes out, and then we use this probability initially to calculate the merger rate with. But as I say here, we need a set of assumptions, and all of these assumptions, they well, they give us a lot of free parameters. We do have good ideas of what can have which value. For example, the supernova kicks cannot be way stronger than, say, 200 kilometers per second for black hole binary, for a black hole, sorry. So we have different ways of narrowing down these possible values, but we can actually also use gravitational waves to narrow down these uncertainties. We can actually just take all of the values and all of the uncertainties, and we predict all of the merger rates. And my former colleague Floor Broekgaarde has done a study like this for black hole neutron stars. And okay, so what we see here on the top x-axis, we see sort of a choice of parameters, and the fiducial is just like the standard. And then each of these is a change in these parameters. It's a one step at a time change. And then we look at the merger rate that we predict to see. And if they go down, then we see, okay, well, this is a negative impact on the merger rate. If it goes up, we have a positive impact on the merger rate. And if it doesn't change that much, we also know, okay, well, this doesn't have that big of an impact. So this parameter is probably not a good thing to go and try to figure out with gravitational waves. If we have a parameter that really changes the gravitational wave merger rate a lot, then we have a lot of, well, hopes or chances that we can pinpoint this with gravitational waves themselves. All these other lines are star formation rates, choices, and there's a lot of things in this plot. So let me go to my latest slides. Okay, I'm going to go back to the mass gap story that I was telling. And so again, so here at the 45 solar mass line, more or less, is this mass gap. But I also showed this GW 1905-21, which sort of is right in the middle of this mass gap. It's difficult to explain. I'll come back to this. So I already told there's a limit to this, to the maximum mass that we can have in a black hole for single star evolution, but also for binaries. So if you have a very massive star, this one, which is at the point that its carbon is fused up, and it now has carbon and oxygen core. If it's at the right size or mass, and that translates in temperature and density, and more or less that translates in the star that has to be higher than 35 solar mass in its core, then this star can become unstable because the temperature and density is just right that the photons that are in there, they can create electron-positron pairs. And because this star is held up in its structure, its hydrostatic structure, by radiation pressure, if you remove this radiation and just fill the star with electrons and positrons, then you will, well, you make the star unstable, and then it will collapse onto itself. And in the worst case, this collapse will trigger an explosive detonation of this oxygen that is there after all this fusion. And this explosive oxygen sort of makes a supernova, which is so strong that it's called a pair instability, and it just explodes the whole star and nothing is left behind. It's a very cataclysmic event, very intense, catastrophic. I mean. There is another pathway. That is when this star is not massive. Well, in essence, where there's not enough oxygen to really explode the whole star. What then will happen is this star will emit pulses. It's called pulsational pair instability, where the explosions are not enough to explode the whole star, but they are strong enough to expel the outer layers of this star. Sometimes in 2 pulses, sometimes in 1,000. Depends very much on the mass of this object. My former master thesis is now a doctor actually. Supervisor worked a lot on this, and when I was in Amsterdam, we worked on this. And so what then happens, it doesn't explode fully, but it pulsates, throws a bit of mass off, and then it cools down with neutrinos. Then it evolves a little bit further and does the same thing a couple of times. And then at some point, it doesn't have enough mass to do this explosion anymore. So what happens then, it will become a core collapse supernovae, and it will turn into a black hole. And in essence, this puts an upper limit on this part here, because if it's more massive, it will just explode, and otherwise it will keep pulsing up until it hits the point that it will go into a core collapse supernova. And more or less, this ends up as a 45 solar mass black hole. Now, this has been done in detail with Rob Farmer and Mathieu Renzo, where for different metallicities, all these different colors, they did this process, and they compared it to the gravitational wave black holes that we found. And this is sort of the limit that they expect to see. And indeed, this most massive black hole is within, more or less, within the error bounds. So this upper limit still holds. And so everything to the left of this is core collapse supernova. Then we have pulsations, and then this pair instability does not leave any remnants behind. So it effectively sets an upper limit. However, their next paper showed that this was not the whole story. The outcome of this is critically, well, it depends very strongly on the amount of oxygen that's available to do this explosion. And one of the uncertainties that we still have in nucleosynthesis as in stars is the nuclear reaction rate between carbon and oxygen. And there's still an uncertainty in this. And if you explore the uncertainties with this, you go sigmas higher and lower, then you actually are able to end up in a situation where there's hardly any oxygen production, and then the star will explode as a core collapse supernova anyway. However, in this case, it results in a 100 solar mass black hole. And so here's this mass gap that we saw sort of the upper limit, but it might be possible to create this. And so in this way, we take this stellar evolution, we sort of explore the uncertainty limits that we have, and then we always find a loophole to make things more heavy. But this is more or less how uncertainties are looked at. Like, how can we create these observations? Are there ways to do this? Well, in this case, yes. However, if we go back to this observation here, there are reasons to believe that this observation actually does not come from this pair instability supernova with a lower reaction rate. There are reasons to think that this comes from a triple or quadruple system in a cluster. That concludes my talk here. I just want to say, like, the gravitational wave era this is the time, this is the moment, and things are going to happen now. We have 50 odd observations, but in the coming years that will increase to 500 and thousands, and at some point it will just keep coming in. And there's a lot of different use cases and science cases that we can use gravitational waves for, objects throughout the whole universe. And even now, the current observations are already presenting us with puzzles that are very interesting to solve, and will certainly place limits on the stellar evolution that we think we know, but surely we have still uncertainties in there. So yeah, thank you. I hope I wasn't overdue with my time too much, but this was my talk.
David, thank you very much indeed. Any questions? I have one, and that is, whilst it looks as if non-manual, or not, sorry, non-physical, or the non-resonant version of measure has been overtaken by LIGO and Virgo, has there been any resurrection of, for example, Mini Grail, to try and see whether they can see any correlation with the output from LIGO or Virgo, or is it that the frequency ranges are so different that that's unlikely?
No, so actually the frequency ranges that these resonant sphere or bar detectors were designed for are the same as the observations that we have now. So they are designed to observe either black hole mergers, or supernovae. The mini grill is still operational. It does not get as much funding as LIGO or Virgo, but it's still operational.
No.
I'm not sure. I'm not on top of my game in this detector field, but I'm sure they will keep doing this and try to make these detectors also suitable for it. Because I'm sure if they just push it and technologically develop these things further, then I think they will be able to. So they haven't given up on them, because there's still 3 operational observatories with that.
Yep. Yeah. Gas members, are there any questions? The usual thing is we're to pose your question via chat, and then I transliterate. I think that was so, well, as you say, this is the right time to be in gravitational astronomy, isn't it? Very exciting. And another of those things where we can't quite touch it, so that the best theories borne out by measurements are still just the best theories, like most of astronomy. How many groups are there across the world working on this particular topic, in your estimation?
Good question, but I think every astronomy department nowadays will at least have a subgroup that will work on this. Yeah.
Yep.
I think they should, because it will be a real new way to observe the universe, and it needs as much manpower as it can get in that sense to create models and predictions of this topic.
Indeed. Any questions? Well, David, thank you very much indeed for your time and your effort. What a lot to take in.
Yeah,
thank you very much indeed.
Okay.
Now, in the coming months, we have in 2 weeks, well, just over 2 weeks' time, 3 weeks' time, our last president, Dr. Paul Daniels, is coming to talk. He's currently a vice president of the Royal Astronomical Society, with special responsibility for mega constellations. And he's going to come and he's going to talk to us about satellite mega constellations and their inevitable impact on amateur and professional astronomy. Thereafter, the following about a month's time, we've got Natalie Rees, another colleague of David's, who's going to talk about asymptotic giant branch stars. And then in June, Professor Raman Prinja talking on outflows from stars. And then in the middle of June, Dr. Susan Cartwright, who was unable to speak to us in February, I think it was, due to a problem with her microwave, is going to be talking to us about supernova neutrinos. Now, hopefully you've all seen there's an April edition of Gaslight. Hopefully you've read it. Otherwise, all my efforts and those of Andy Andrews and Martin and others have been to no avail. And if you feel moved, as ever, please write something for the next one. So, meanwhile, keep safe, all the very best, and thank you for your attention.
All right, bye-bye.
Bye-bye.